In this video, we're going to present the solution to section 3 from the December 2016 exam, and that's an optimization problem trying to maximize the profit for manufacturing an LCD panel. There's a number of constraints built into this. In particular, we're told that this is an old school 4:3 ratio for the width to the height. Typically they're 16:9 in today's markets, but this is an older model. And we have two elements. We have a price that depends primarily on the diagonal dimension of this screen. And we also have a cost that's based on the area. So as we increase the area, it gets more expensive in a linear way, or to the square root of the area rather. And as we increase the diagonal size, then we can sell it for more with a higher price. What we're looking for is the sweet spot that maximizes the profit. And if we're trying to compute this, then of course what we need is a function for profit. And we need to then write that out. Well, it's price minus the cost, or manufacturing M. And we have formulas for each of these to start with. So let's put those in as building blocks. And those are just copied from above. Then we have to recognize what the challenge is. If we're trying to maximize profit, we have to recognize what we can control. And we can control the diagonal and the area, but we can't pick them independently. If we change the area and we have a fixed ratio, then we're also changing the diagonal. So the problem we have to address is reducing this down to only one variable. That's something that we have to do before we can tackle this with our standard derivative operation. So how can we work with that? Well, what makes sense, especially given that we have this relationship between x and y and area and diagonals, is build some of those relationships out. So one of the things that we might want to look at is the diagonal. Well, the diagonal is related back to x and y through a Pythagoras relationship. It's the square root of x squared plus y squared. We also have the area, which is in our formula, and that is x times y. And last but not least, we actually have the relationship between x and y. X over y is equal to 4/3. With those ingredients, we should be able to boil down the profit calculation into something that involves just x or y, as those seem to be the building blocks for the entire expression. Let's focus on making things in terms of x. So in particular here, we could write that y, if we bring it up here and bring the 3/4, y will be 3/4 of x. If we number these equations, 1, 2, 3, and then this form here being 4, we can sub 4 into 1 to see if we can simplify our diagonal calculations. Well, our d will be equal to the square root of x squared, leave that where it is, plus y squared, but y is 3/4 of x. So we'll have 3/4 of x all squared. That we can leave as is, but anytime we're going to be taking a derivative, if we can simplify things, it's really to our advantage. This is correct, but not simple enough to be easily worked with. So let's try to tidy that up. And that'll be x squared plus, expanding this, 9/16 x squared. And that we can put on a common denominator of 16. We'll have the square root of 16x squared plus 9x squared all over 16. That'll give us 25/16 x squareds, and that is much nicer. We can take the square root of every single factor there, and we end up with d is equal to 5/4 of x. And that is going to be a lot simpler to work with than any of the earlier expressions we had. So that's step 1 complete. We have d in terms of x. Our next stage is to see if we can get the area in terms of x as well. So let's take a look and use number 2, which is area equals x times y. And then we'll use our equation 4, which tells us that the y value can be replaced by 3/4 of x. And so we have 3/4 x squared. Putting all these ingredients together now into the original price, or profit rather. Let's give that a new name. We've already used p, so let's call this q of x as the closest letter. It's 20d minus 1 over 576a squared, but we just found out that d was 5/4 of x, and the 1 over 576 stays, but a is 3/4 x squared, and the cost function for manufacturing involves squaring that again, so we end up with 3/4 x squared all squared. Again, we're going to be differentiating that, so it makes sense to take some time to tidy that up. 20 over 4 is 5, that'll be 25x, minus, when we expand all of this out, and here using the fraction button on your calculator can be a real handy device. We have 3/4 squared, and that 3/4 squared then is divided by, or multiplied by 1 over 576, and we end up with 1 over 1024 x to the 4. Perfect. That is a lovely function to differentiate. So to maximize, we're going to look for critical points, pardon me. Look for critical points. That's q prime of x equals 0, but q prime of x is equal to 25 minus 4 over 1024 x cubed. Label this clearly as we're setting this equal to 0. And if we do that, we're going to end up with a nice simple equation for x. Particularly move this to the other side, we'll have 4 over 1024, that's just 1 over 256, x cubed equals 25, x cubed equals 25 times 256, or x cubed equals 6,400. Perfect. That gives us x equals the cube root of 6,400, which is around 18.57. All the units here were centimeters. That's right, all the units here were inches. So 18.57 inches. Perfect. And we have y, which is equal to 3/4 of x. That's from back up here. 3/4 of x. And that gives us a height of about 13.92 inches. Now we were asked to fill in the other blanks here. What's the diagonal? Well, the diagonal, we had a nice simple formula for it. The diagonal is 5/4 of x. That ends up being 23.21 inches. And last but not least, the profit that we get is 20 times the diagonal minus, what else did we have? We had our function here. We could do it with x's or we could do it with the diagonals. Let's do it with the x's here because we have that value over x to the 4. And if we calculate that out, we get $348.12 approximately. So we just write those final values in our table, and we have completed the problem. We should double check though that we actually have answered all the details in the question. So going back to the top, there's nothing here about evidence that we actually have a maximum of profit. There's only a single critical point that we found. So if we only have a single critical point, it's likely the most interesting one for our problem, which would be maximum profit. So we'll take that as a given here. In other problems on other exams, potentially this year's exam, we may ask for evidence from the first or second derivative test for local maxima or minima, or we might ask for evidence that something is a global max or min. So just be aware that that could be part of the requirements as well. It's not required here in this question. If it is required, it'll be explicitly stated in the problem. And that is question number 3 done.